Hello students, in today's lecture we are going to derive the relation between gamma and beta function. The relation between beta and gamma function is beta mn equals to gamma n upon gamma m plus n, where both m and n are real numbers. So starting from the definition of gamma function, we know that gamma n equals to integral from 0 to infinity e power minus x to the power n minus 1 into dx. Now put x equals to zy. This implies that dx equals to z dy. In order to check the limits, if we are going to make substitutions, so when x equals to 0, y will be equal to 0. When x equals to infinity, so y will be equal to infinity. So there will be no change in limits. So we can now make substitution. Therefore gamma n will be equal to integral from 0 to infinity e to the power minus x, which is zy, into x to the power, which is zy, to the power n minus 1 into dx, which is z dy. Now we can write it as integral from 0 to infinity e to the power minus zy, and here we have z to the power 1 and here z to the power n minus 1, so both will be z to the power n and y to the power n minus 1 into dy. Bring this z to the power n out of the integral, so it will be z to the power n into integral 0 to infinity e to the power minus zy, y to the power n minus 1 into dy. And we can also write it as z to the power n integral from 0 to infinity e to the power minus zx and x to the power n minus 1 into dx. By the property of definite integral, we know that this is actually an integral from a to b. F of x dx can also be written as integral from a to b f of y into dy. So I have made this property. This is equation number 1, which is gamma n. Or I can also write it as, let's suppose, bring this z to the power n to the left side, so it will be gamma n upon z to the power n into integral, which is equal to integral from 0 to infinity e to the power minus zx x to the power n minus 1 into dx. This is equation number 2. Now using equation number 1 and multiply both sides, of equation number 1 by z to the power m minus 1 and e to the power minus z, and then integrate with respect to z, from z equals to 0 to z tends to infinity. Therefore, equation 1 will now become like this one, which is gamma n into e power minus z, z power m minus 1 into dz, integrating from 0 to infinity, which is equal to integral from 0 to infinity e power minus z, z to the power m minus 1, and this will be z to the power n into integral from 0 to infinity e power minus zx, x to the power n minus 1 into dx and dz. Now this is actually gamma n, and this is actually gamma function for m, so this can be written as gamma m, which is now integral from 0 to infinity for the z, and now bring this integral also here, which is integral to 0 to infinity e power minus z, and here we have also e power minus zx. So taking z out of here, this is 1 plus x. When these two terms are multiplied, so the powers will be added, which will be e to the power minus z minus zx. So minus z is taken common from the power, and now z to the power, here we have m minus 1, here we have z to the power n. Clear? So it will be z to the power m minus plus n minus 1, and x to the power n minus 1 dx dz. So here we have this integral with respect to x, and this one is with respect to z. So changing the order of integration, we can write it as gamma n, gamma m will be equal to integral from 0 to infinity. So here first the integration was with respect to x, and after that it was with respect to z. So first now we are integrating this term with respect to z, so taking this before the z integral, which is x to the power n minus 1, and integral from 0 to infinity e power minus z into 1 plus x, z to the power m plus n minus 1 dz, and then dx. Now this can be also written as integral 0 to infinity x to the power n minus 1, and this is actually the integral, this integral is actually the gamma function of gamma m plus n upon 1 plus x to the power m plus n, and here we have dx. If you students remember during the gamma function lecture, we had properties of gamma function. Dx. This term here is actually a resemblance of equation number 2. This term came by using equation number 2. Look at these two integral, students. Here we have integral from 0 to infinity e to the power minus zx, and here we have 1 plus x, and here z to the power n minus 1, and here is m plus n. So this is actually gamma function of m plus n. This integral is gamma function of m plus n upon z to the power n here we have, and here we have 1 plus x to the power m plus n. Clear? So this integral now becomes in the form which is gamma n gamma m is equal to, take this gamma m plus n out of the integral, gamma m plus n into integral from 0 to infinity x to the power n minus 1 upon 1 plus x whole to the power m plus n into dx, or bring this gamma m plus n to the left side. So therefore this will be equal to gamma n gamma m upon gamma m plus n, which is equal to integral from 0 to infinity x to the power n minus 1 upon 1 plus x whole to the power m plus n into dx. That this is equation number 3. Now, if you students remember, in the previous lecture of beta function we had a property. We proved this transformation of beta function by using beta mn. In that lecture we had these constants were lm, but here instead of that we have mn, and that was equal to integral from 0 to infinity x to the power n minus 1 upon 1 plus x whole to the power m plus n into dx. So we can write this, replace this integral by beta mn. So by from 3, equation number 3 and 4, we have proved that gamma m gamma n upon gamma m plus n is equal to beta m into n. So this is the relation between gamma and beta function. Now in this problem we are asked to show that the integral from 0 to phi upon 2 sine to the power p of theta and cos to the power q of theta d theta equals to gamma p plus 1 upon 2 and gamma q plus 1 upon 2 divided by 2 times gamma p plus q plus 2 upon 2. So by definition of beta function, we have beta mn. It can be written as integral from 0 to infinity x to the power m minus 1 into 1 minus x to the power n minus 1 into dx. Here both m and n are real numbers. Let this is equation number 1. So you can write any constants here. We have mn, pq, lm, whatever we have. So everywhere we have a value, we should write that value here, and instead of n we have write it there. Put let's make some substitution. Put x equals to sine square of theta, and its derivative will be dx equals to 2 times sine of theta cos of theta into d theta. Now we have made some substitution, so we have to check the limits for limits. When x equals to 0 in this equation, so solving it for theta, here in this equation the variable is theta, so when we put x equals to 0, then theta will be equal to sine inverse of x under the root, so that we will get theta equals to, therefore theta will be also equal to 0. And when if we put x equals to infinity, I'm sorry, I made a mistake here. This is in this equation the limits of the integral are from 0 to 1, not from 0 to infinity. I'm sorry, this is 0 to 1. If we put the limits, the upper limit 1, then this theta will be equal to phi upon 2. Therefore beta mn will be equal to the integral from 0 to phi upon 2, and instead of x we have to write sine square theta, that is sine square theta whole to the power m minus 1, and 1 minus sine square theta whole to the power n minus 1, and d theta is 2 times sine of theta cos of theta and d theta. Now this one is, this 2 will come here, 2 times integral from 0 to phi upon 2, and I can take this 2 here to multiply it with m. This will be sine theta whole to the power, for instance let's write it here, sine square theta to the power m minus 1, and we know that 1 minus sine square theta equals to cos square theta, so this will be cos square theta to the power n minus 1, and sine of theta cos of theta d theta. Now multiply this square with the upper power, this will be integral from 0 to phi upon 2 sine of theta whole to the power 2m minus 2, clear, and this will be cos of theta to the power 2n minus 2, and sine of theta cos of theta into d theta. Now this will be equal to 2 times integral from 0 to phi upon 2. Here we have sine of theta and here we have sine of theta, so their powers will be added, so it will be sine of theta to the power 2m minus 1, and cos of theta to the power 2n minus 1 into d theta. Now sitting, this one is beta mn. 2m minus 1. Here this value, let's suppose may call it p. So this will lead us that m will be equal to p plus 1 upon 2. And similarly 2n minus 1, let's call it q, then n will be equal to q plus 1 upon 2. Therefore and by the property, let's call it this equation second, and by the relation of beta and gamma function, we had beta mn is equal to gamma n upon gamma m plus n. So using equation 2 and putting this value in that equation, so we will have this will be gamma m. Here we will write gamma mn, and if we write value of m, this will be gamma p plus 1 upon 2 gamma q plus 1 upon 2 divided by gamma, this will be m plus n, so it will be gamma m plus n plus 2 divided by 2. Clear? So it will be gamma p plus 1 upon 2 gamma q plus 1 upon 2 divided by gamma m plus n plus 2 upon 2. So this will be equal to 2 times integral from 0 to 5 upon 2 and sine theta to the power 2m minus 1 is p, cos of theta to the power 2n minus 1 is q into d theta. Or bring this 2 to the left side, it will be gamma p plus 1 upon 2 gamma q plus 1 upon 2 divided by 2 times gamma m plus n plus 2 upon 2, which is now equal to the integral from 0 to 5 upon 2 sine of, I can write this p when this p is multiplied here, so it will be sine of to the power p of theta, cos to the power q of theta, and d theta. Or right this side before, this will be integral from 0 to 5 upon 2 sine of theta to the power p cos of theta to the power p to the power q, and d theta which is equal to 1 over 2 gamma p plus 1 upon 2 gamma q plus 1 upon 2 divided by gamma m plus n plus 2 upon 2, so which is the required result. Here we had to prove this equation. Thank you very much.